Okay, good evening, everybody. I'm going to be talking about the next chapter of our meeting, which is an update on the night sky, solar activity. And I usually give an update on meteor showers, but today we're going to blend that into our discussion of the Perseid meteor shower, which is arguably the most famous meteor shower that there is. Okay, so we're at the tail end of summer here. So the days are starting to get shorter. Sunset tonight is around 8:13 p.m. And every night it's about a minute or so earlier. Astronomical twilight and is basically the time that the sun is at the 18-degree mark below the horizon, which is the beginning of the darkest part of the nighttime. That time is getting slightly shorter for us observers at night. In terms of July, we have the full sturgeon moon. So I like to talk about like which particular moon from the Farmer's Almanac, the name full sturgeon for the famous fish of North American lakes, and some prominent constellations that you could see during this time of the year, constellations and asterisms. One of them is Cepheus the King. So Cepheus is in the night sky, in the northern night sky next to Polaris. You could find it also in the vicinity of Cassiopeia. So we find these patterns in the vicinity of each other, and that's how we slowly but surely memorize the night sky. I usually don't go by constellation. I go by maybe a collection of constellations necessarily. So if you recognize that Cassiopeia is opening up towards the north, the W or the M, and Cepheus is always going to be between the two. Continuing forward. By the way, the reason why I'm starting with constellations is the summertime is not the best time of the year for observing planets. Usually you have to be watching the horizon either in the evening or in the early morning to observe the planets, versus entering into fall and winter time. The depths of winter is really the best planetary season because you just step outside in the middle of the night and the planets are, generally speaking, in the northern hemisphere, at least right above our heads. So another asterism in this case is the Northern Cross, which is a subsection of Cygnus. So just like the Big Dipper is not a constellation, it's an asterism, but it's a subsection of the Big Bear, Ursa Major. The Northern Cross is a subsection of Cygnus the Swan. So the Northern Cross is composed, Deneb being the brightest star there at the Northern Cross point. It's also the same star as one of the three triangle stars of the Summer Triangle. So Deneb actually shares two asterisms, very famous asterisms, the Northern Cross star, as well as one of the three major stars of the Summer Triangle. And then the Summer Triangle itself, you can find with, you can actually use this triangle to observe constellations that you might be less familiar with. Okay, so for August planets, there are none. So just saying, no, I wanted to go through how you could observe some of these planets, even though it isn't the best season, that's often said. There is an opportunity to see them. And this is, in terms of time, you have to be willing to get up early and find, more importantly, a view of the horizon, which might be very hard, especially on flat sea level land like we are with shrubs and buildings and such. But if you can, it would be pretty interesting to see some of these. So Jupiter basically will be near Aldebaran, looking east. And basically it increases in its rise above the altitude throughout the August. So it rises starting right now about 2 hours before sunrise. And by the end of August, it's about 4 hours before sunrise it starts to rise. Mars also, so Mars is here, Jupiter is here. So you can see August 1st to August 31st, it's the same situation where we get earlier and earlier rises of Mars. I put the magnitudes there next to the name, so M being 0.7. Anything that's less than 6, you can see with the naked eye if you have a visible, if you have a view of it, essentially. Saturn is something interesting that maybe you might not be familiar with its rings, but the rings, of course, they change. That's our viewing angle changes. And right now we have a closing ring system, meaning the rings are getting smaller and smaller until they disappear. And that will be in March 2025 when they fully disappear for a while. It will visit the moon on August 21st. If you're in Latin America, the Caribbean, South America, and part of Africa, you'll actually see the moon occult and pass in front of Saturn, which is a really cool opportunity for astrophotography. Unfortunately here, it makes apulse, meaning it gets close, but it doesn't cover it, and then it moves on. So That'll be August 21st. And it starts to rise earlier before sunset. So opposition, September 8th, opposition is when we pass between it and the sun. So it's in its best viewing angle, at least for us. And so September is really good for Saturn. And then as it gets later into the year, Jupiter takes over Saturn as the king, kind of like how Jupiter overthrew Saturn in Greek mythology. It's same kind of deal. With Venus, Venus is a very late riser. So 30 minutes after sunset is the last opportunity, basically the only opportunity you can see it. And it doesn't get that much higher in the sky. It will be near the waxing crescent moon this evening. So actually, it's already passed at this point, probably, where it's right on the horizon. But basically, the crescent moon, I like to show these alignments because they're really good for binocular viewers, or if anybody likes to do astrophotography and have a very interesting shot. And then for Mercury, Mercury is nearing its conjunction with the sun. So conjunction is opposite to opposition. If opposition is the best time to view something, conjunction is the worst time. Mercury undergoes conjunction twice. Mercury and Venus undergo conjunction twice. The rest of the planets only once. Can anybody explain why? Maybe if they can think about it. I don't know if they want to take a guess at how that works. What's the difference between Mercury and Venus and the rest of the planets?
Mercury moves faster?
Mercury definitely moves faster. Venus is the second fastest, so that's correct. But that's a consequence of the deeper thing. Yeah, they're within Earth's orbit. So Mercury and Venus can pass in front of the sun or behind the sun. Inferior conjunction, superior conjunction. Versus a big planet, one of the outer planets, they can only pass behind the sun from our perspective. Okay, so Mercury is nearing its conjunction, meaning it's basically going to disappear until the end of August. Mercury is the fastest planet, so whenever it disappears, it comes right back. Mercury is the messenger god, so it is going to be the fastest in the sky. Okay. Now let's talk about some solar activity, okay? I wanted to touch on a point here. These are noctilucent clouds, which is basically a collection of meteoroid and cometary debris floating in the upper mesosphere, so the third layer of the atmosphere, getting bombarded by solar particles. So it's essentially like the dust of the meteors act as seeding for clouds. The water vapor and other types of molecules condense around those particles, and then when solar rays hit them, they become excited and give off light. This has been increased due to rocket activity. So actually we see a direct correlation with that. It's published at this point. Right now we're reaching solar maximum, which actually is deleterious to this effect, meaning when solar reaches maximum, we actually see the noctilucent clouds get burned away essentially. But for whatever reason, we've seen the strongest noctilucent clouds in years. And there has been two significant things to cause that. One is the significant increase of rocket launches, which is cool because those actually look pretty cool. So I can get behind that, at least their effect. And the other one is the Tonga eruption that happened a few years ago that actually released enough particulate matter into the upper atmosphere to still be there and cause a noticeable change as well. So we are experiencing a very active sun, and it's the highest in 23 years. So since 2001. 2001 was the last time it was this active, and we're still not done. By next summer, we'll actually be at solar maximum. Right here is, sorry, I almost did it again, a sympathetic burst. There's a burst and then another burst shortly after on the limb. That's been happening a lot. They're connected by the magnetic fields. There's actually very complex magnetic fields on the surface of the sun. It's not simply a bar magnet with north and south. There's actually many dipoles sticking out of the surface of the sun, moving, and it's very complicated actually. But when they're connected, they can actually trigger an explosion on the far side of the sun, or the limb in this case. So how do we know that activity is increasing? There's a couple of ways that I'll show you. One is to observe the sun very carefully every day and to count sunspots. So you look at the surface of the sun at the same time every day, you count the number of spots you see on it, and you just plot it. And we've actually been doing that since the early 1700s. And you see there's actually a very interesting pattern, a very regular, right, amplitude-wise notwithstanding, the frequency is very regular. It's 11.5-year cycle. And so much so that we can actually predict, right? The purple is a fit, the red is a prediction, but we can basically predict the activity of the sun based on counting sunspots. If we zoom in on the plot, this is why we're nearing solar maximum. The red is what the prediction is. The gray is the tolerance in the model, and the black line is the observation. Look how high up that spike is above the expected rate. So the sun is unusually active right now. It's arguably Carrington level, the famous Carrington level event that happened in the mid-1800s. We actually experienced the May 10th eruption, which was in similar magnitude to that. Okay, so that's cool. The other thing is, this is something I never explained before, but I wanted to bring it up here, is you don't know, this is a more modern version of it. So sunspot counting has happened since the 1700s. And since the 1950s, we've been measuring the radio waves coming from the sun, and we noticed that there's a direct proportionality between the number of sunspots on the x-axis and y-axis being the flux, or let's say the brightness of the radio light coming from the sun. So we know that the sun in two ways directly, that as the sunspots increase, it becomes more radioactive, well, not radioactive, but radio emission. And then on quiet time, when there's no sunspots, there's not as much radio emission coming from the sun. It's a modern version of counting sunspots. And this is pretty cool. I like this a lot. So in terms of solar activity, there has been, this is a very recent image, only a couple of days ago. So sunspots are numbered. AR 3780 is this particular one. This is huge and it's growing. So every few hours we see this actually growing on the southeastern limb, and it's going to move over the course of 2 weeks. So if you're looking at me and I'm the sun, it's up here. It'll start to pass in front of us, and this is when it's most dangerous because it's pointing right at us, and that takes 2 weeks about. And so it likely poses a threat for strong flaring activity. If the sunspot's looking at us and it blows out this way, that will cause a lot of issues for Earth technology and life as well.
I have a question.
Yeah, please.
And you've mentioned this in prior talks, but
Yeah.
if you could, what is the physics that underlies the periodicity of sunspots?
Yeah, that's a good question. Actually, it's a very deep question because it wasn't understood. Let me see if I can, probably the next slide, which I was going to show you anyway. There's a couple of features here that kind of link to that. So the sun does not rotate like a rigid body. It's made of plasma. And so that same centripetal acceleration that Blaine was explaining about the equator of the Earth, that actually causes differential rotation of the sun. So the equator actually rotates faster than the poles. And you can imagine maybe if you let that go after a while, that kind of can get a little messy because your equator starts to spin and cause drag forces. Well, the magnetic field of the sun is immense, right? And so these magnetic field lines, you can't see them, but they're actual physical lines of force. So, they might seem magical, but they're actually a physical thing, not unlike a physical object. And so these get wound up around the sun, kind of like a knot, it gets tighter and tighter and tighter. And when it reaches maximum, the tension, basically it can't retain it anymore, and it rapidly spins the other way, disentangles. And that tangling in one direction, and then tangling in the other direction is every 11.5 years. It explains why sunspots appear in pairs. It explains why one of those sunspots has positive polarity and one has negative. And they usually appear predominantly on the south or the north, and that oscillates as well. So all of these observations of sunspots appearing, disappearing, appearing up here, always appearing in pairs over the decades has to be explained by a model. And the most successful model is it's called the solar dynamo model. Magnetic field lines get wound up, and then when they reach maximum tension, when they unwind, they release all of their energy. And so that's why solar maximum is at the point of maximum tension. Okay. Still unsolved and potentially has a Nobel Prize level reward for the deepest theory that can come out of this still. So there's that new sunspot coming out on the southeastern limb that will swing out over the next few days, and it's been growing. So that's something to keep a lookout for. Yeah.
I can't see that asked question. It might have been a while before about planets.
When should we be able to see planets at nighttime again? Yeah, basically in the next month. So by the end of August, September is really the beginning of that season for planetary viewing, and it gets better and better through December. So usually fall is when I say to start brushing up on celestial navigation and looking for the planets. They'll start to make a better appearance by the end of this month. And then September is really the beginning season for that.
That's already coming up.
Yeah.
Like 11, 11:30.
Yes. Saturn always rises first through the season and then starts to set as Jupiter overtakes it, and then Jupiter becomes basically king of the winter. So I like that how it's encoded. I don't know if I don't know which came first, that or the myth, but that Jupiter overthrew his father Cronus, which is Saturn in Roman mythology. So I don't know. That's really interesting. Okay, just want to keep my eye on the time here. So another thing we can look at for solar activity is its atmosphere. So the visible surface of the sun is called the photosphere. The atmosphere of the sun, there's a local atmosphere called the chromosphere, and then there's the outer atmosphere, which I don't show here, and extends millions of kilometers into space, called the corona. That's what you see during an eclipse. So in terms of the corona or the chromosphere, right, the kind of the equivalent of the atmosphere, whenever we see holes, which are the dark spots, holes inside the atmosphere, that has a potential for releasing surface radiation and particles through that atmosphere. The atmosphere is good at blocking those, but when a hole is open, that solar wind can pour out and cause, it mainly causes radio issues and telecommunications issues. The more dangerous things are when the sun actually causes a coronal mass ejection and actual protons and particles come flying out of the sun in large mass. And finally, the most recent coronal mass ejection was August 4th, yesterday, and it caused, so there's different classifications for geomagnetic storms. The worst is an X class. A G class is the second worst, so it's not as bad, but a G3 is pretty strong, and it caused aurora. This is aurora seen in association with the CMA in California, Colorado, New Zealand, and China. And so, and these are pretty bright aurora. You could see like, I mean, there are stars in the sky, but for the aurora to essentially be seen that low in latitude is basically how we just tell how strong the solar storms are affecting us. So you can look up, NOAA not only has a weather forecast and a climate forecast as well, but it also has space weather forecasts. And this is a prediction of how much aurora there are, right? The stronger the aurora, the more farther down the Earth they descend, okay? So right now it's pretty quiet, but if a coronal mass ejection hits us, then it becomes strong or unsettled. And then that's why you can see aurora all the way down in somewhere like California, which you can see is kind of ridiculous. That's far down, right? So that's a G3 class storm. If the strongest type of storm hit, you could see aurora down to probably Texas, which I believe has happened once. Yeah, please.
It's like, I have like, I want to find out, is this like the only thing where it's like super far down the forest where it connects to which like changes the atmosphere?
Well, that's a great question. No, actually, it's not. And in fact, the sun's been weirder in the past. So even one of the most prominent ancient sunspot viewers, which were the Anasazi in New Mexico, they stopped following the sun and basically broke down camp and abandoned that spot when they noticed that the sun had sunspots that they could see with the naked eye. So sunspots can actually grow to considerable size. They said that the sun was pockmarked or it had leprosy or something like that. And we know that at that time, the sun was very active in the record. You can tree rings and other types of coring sampling is consistent with the solar change. And so that's way more than even now. Like that would cause aurora probably down to it could go down to the equator potentially. The Carrington event, which was in the 1800s, that is roughly the same magnitude of activity we're seeing now. I think the mid 1300s. It's coincident with the little ice age of the Middle Ages, why everybody started to get plague. Crops failed for years. It was because combination, well, we don't know about volcanic activity, but we know that the sun around the world, every culture was talking about this time between 1300 and 1350 or so. So the Anasazi is seeing the sun change in appearance and the crops just suddenly fail after centuries. And that happened in Europe as well, and in China. So that's ancient astronomy is very interesting. No, Galileo looked at it through a telescope. That was before solar filters. So yeah, and he went blind. Back then, like what was their I mean, it's hard to tell what the interpretation of an ancient culture had of like certain phenomena. We just have what they kind of wrote and the allegories they used. And in this case, yeah, it's not really easy to tell if they really understood like, oh, there's a strong magnetic field on the surface of the sun, and like if they had that explanation or not. That doesn't mean that they were any less sophisticated than we are, though. They just had what they were working with, right? So. Okay, last part of this talk will be an extension of the meteor shower bulletin. As the Perseid meteor shower, that is an image of a Perseid that somebody was taking a picture, this was last year, of the Andromeda galaxy, and a Perseid shot through their camera image. So instead of Starlink or instead of a satellite, they have Perseid. The green color is because we're in the mesosphere, so you have an excess of nitrogen rather than oxygen. Most of these burn up about 80 kilometers above your head, and they're the size of pebbles. So they're just moving considerably fast. That's why they burn up. So the Perseid meteor shower, it's prolific in the sense that it might arguably be the most famous of the meteor showers. It's associated with a famous comet, Swift-Tuttle, and is visible from mid-July to August. So we're actually entering right into the peak activity right now. This was posted a couple of days ago. Delays up to several hours. Joshua Tree National Park braces for visitor surge. Just like the eclipse, right? Something changes in the sky and humans get all like weird, and it's like it affects us and actually changes our behavior. It's a very interesting behavioral phenomenon. So in this case, it's with meteor showers. Comes from the Greek word, right? So in terms of, this is Perseid, or I'm sorry, this is St. Lawrence, right? So it comes from the Greek word Perseidae, and it means the sons of Perseus. It's also known as the Tears of St. Lawrence. So there's some interesting lore. I won't go into detail about it, but there's basically some lore behind this meteor shower that is very interesting the more you delve into it. Its radiant is in the constellation Perseus. So they're named Perseids because of the location from which they emanate from the sky. It's bordering Cassiopeia and Camelopardalis, and it's primarily visible in the northern hemisphere. So it's actually a really good northern hemisphere meteor shower. So the Perseid meteor shower peaks sometime between August 9th and 14th, although it's never exact. That's why every year that forecast changes a bit. In this case, it's predicted to be in the pre-dawn hours of August 11th and 12th, 12th or 13th. Basically, it's not an exact number. It's not like there's one point in time where it's at its peak, right? So it's primarily visible in the pre-dawn hours. So you're going to want to get up to view these between midnight and 5 a.m. The reason is because the direction of the Earth it's kind of sweeping up more meteor debris as it's moving. And since the Earth rotates in the direction of its motion, we're sweeping up more in the forward stream. So that's why in this particular case, early dawn is the time to view these things. Most of these, I think I said before, they burn up very high in the atmosphere, about 80 kilometers or so, but they're very bright. They're also very fast as well. So they move, these are considered swift movers, 60 kilometers per second. So you can imagine something about the size of the cross-section of this lid here or smaller moving at 60 kilometers per second. But then they basically have a zenith hourly rate of 60 as well. What does that mean? That means if they were all coming from the top of the sky, the darkest part of the sky, the thinnest part, that's what the rate would be, the zenith hourly rate, the amount per hour we would see if it came from the zenith. And so you can expect to see, if it's dark enough, you can see tens per hour. So you'll see streaks every few minutes, essentially, in some cases. This is over the course of only 2 hours exposure. This is like, I believe this is 1998, 1997 or 1998 Perseids. And so just within an hour, you can see kind of where the radiant was. But if you counted all of these, this would be a couple dozen probably. So you can, this is a very prolific one, very active meteor shower. Okay, so it comes from this comet right here, 109P Swift-Tuttle. It was one of the first comets I actually studied when I was a kid, because I liked this one in Temple-Tuttle. So the couple of the different meteor streams. I always liked this one. But basically, just for some reference, a comet has a nucleus, it has a coma, and then it has 2 tails. I won't explain why it has 2 tails unless somebody has a better explanation. And it's basically this comet right here, Swift-Tuttle. It's a periodic comet. periodic comet is different than a long period comet. So what does that mean? It means that it has an orbit of at least less than 200 years. In this case, it's got a 133-year orbit. And Jupiter has actually been tidally interacting with it and sweeping it up. So it's locked into a resonance, meaning it completes one orbit for every 11 orbits with Jupiter. And it's huge. It's got a 26-kilometer diameter nucleus. This is an image of it taken actually quite a long time ago. And this is a plate exposure of it. And so this is a really interesting comet to study in of itself, just the source of the meteor streams that we're seeing. So Swift-Tuttle has been observed for quite a long time, and it was actually lost because 133 years, every 133 years it reappears. And so comets and asteroids are actually lost all the time. The ones that are lost more often, unfortunately, are the Earth-crossing orbit ones, the ones that are small and quick. So highly uncertain orbits. So if you lose that sight of them, it might be hard to ever find them again because their orbits are constantly changing. So in this case, Chinese records are very reliable. Once again, very, very reliable, actually. Probably the best in antiquity for this type of observation. We know that in 69 BC and 322 BC, it had about a magnitude of 0, which is equivalent to the star Vega in the sky. When they say it's discovered, right? So I just said that it was observed hundreds of or thousands of years, but it was discovered by these two gentlemen here in the 1800s. What that basically means is they were able to calculate its orbit and start to make predictions of its reappearance, right? The discovery of a planet, for instance, if you discover a planet or an asteroid, that means you've shown something is moving between two images in the sky. You then, from that data, predict where it will be in the third image. You take an image and it's there. That's kind of considered basically the discovery criterion. So that's what they did as well. The last major apparition was seen in 1992. This is astronomer Camuccio. He's actually an amateur astronomer. The amateur astronomers are the best at these types of observations. So this was 1862 plus 133 years would be about 1995. So that's the last time it made its close appearance. Unfortunately, like we won't be alive when it's making its next close appearance. But it was caught about 8.6 AU from the sun, and that's the last it was seen. So its next apparition will be in 2126, and it'll be just as bright as it's been predicted for a while. So it would be very bright on the sky, a naked eye comet. I don't know if anybody's ever seen a naked eye comet. They're considered great comets, but they're rare, and you're very fortunate to see one of them. That animation is painfully slow, but basically what you would see over the course of days is this would descend. And I'm hinting at something here because it's a very well-studied object for a reason. Maybe you can tell already because look how close it is getting to the Earth, right? It's a 26-kilometer rock, or it's a dirty snowball, but it's 26 kilometers moving 60 kilometers per second. So you have something 5 times the size of Brownsville moving 20 times the speed of a bullet, and it gets within a few decimal AU of the Earth every 100-something years. And we lose it sometimes. So it's like, this is it's actually considered the single most dangerous object for humanity. And I have physics to back this up, more than all the nuclear bombs combined. This would be 27 times the Cretaceous extinction event impact energy if it hit. I'm not trying to scare you because it gets within 0.0009 AU of the Earth, 130 kilometers, or within basically the relative distance to the moon.
130,000 kilometers.
130,000 kilometers, correct. What did I say? 130 kilometers? Yeah, I was just speaking quickly, I guess. 130,000 kilometers. And so this was pretty much the reason why it started to be heavily studied when it reappeared. It was predicted to reappear, but the date was off by weeks. And that's bad. That means that it's highly perturbed. And that means that if you lose sight of it, you could potentially not get it back until it's too late in this case. So there was a fear of an impact of this object on its next perihelion passage in 2126. But actually additional observations indicate that there's no threat. When I say additional observations, that's loaded right there because there have been very extensive observations of this comet. Actually, the meteor shower itself is useful for understanding parts of the comet as well. So it most likely will pass Earth and it won't hit us. But predicting a comet 100 years out or the orbit of something 100 years out while all the planets are pulling on it. It's very difficult. So you got to take these numbers with a grain of salt. So all I can say with that is keep your eyes to the skies. So that's all I'll say about the comet. I can take questions. I didn't want to take too much more time. This is a picture of what it probably would have looked like in 1862. So pretty cool. And they have observatories. They have mini domes just like CTMO as well. So maybe we can do some viewing at CTMO next time. So thank you very much. Sorry for all the technical and human difficulties. Any questions or any comments or complaints?
So, because I heard a couple, both ways, but you said the radio, like, first, the constellation. I've been, right?
The radiant is Perseus. Yeah. Sorry, I just wanted to. Yeah, you should be. I mean, you don't want to like look at the spot that it comes from, because as they enter, they're moving so fast that they start to burn up like through the longest path length through the atmosphere, right? They're kind of they're intersecting the atmosphere. So they're not going to immediately burn up at the radiant point. They're going to burn up fractions of a second after they enter the atmosphere. So really what you want to do is use your peripheral vision for comet hunting, honestly, or meteor shower hunting. The best would be to frankly lay on your back if you have a good view of the sky and use your peripheral vision, and you'll catch them all the time. If you're doing astrophotography, you can kind of point to the radiant, but maybe off axis have the radiant over here and take a very long exposure, and you'll catch them going through your camera over long exposure. But yes, generally speaking, you don't want to look at where they're coming from in the sky. You want to kind of get a very big area with your peripherals. Yeah. Maybe everybody wants to take a break. What's next? Is that it? Okay. Well, thank you, everybody online.